Hello everyone. I'm Young Kim from Naver Cloud and Coarse. This is our ECCV 2026 paper, Phoenix, Semantic-Aware Mask Refinement through Adversarial Perturbation. Even state-of-the-art segmentation models produce masks with imperfect boundaries, semantic confusion, and structural errors. Mask refinement turns a coarse mask into a high-quality one, without retraining the original model. But existing refiners, like SegFix and SegRefiner, are trained on synthetic noise made by simple morphological operations, random dilation, and erosion. This noise is spatially random and content-blind, so it fails to capture how real segmentation models actually make mistakes. Our key idea: what doesn't kill you makes you stronger. We repurpose adversarial perturbation, normally used to break models, as a constructive tool for generating realistic training noise. Instead of blind geometric operations, we attack the mask decoder's own embedding space. This concentrates the noise exactly where the model is uncertain, at semantically challenging boundaries and ambiguous regions, producing far more realistic errors. Phoenix builds on a frozen SAM encoder and fine-tunes only a lightweight decoder. It has two core components. Adversarial mask perturbation, or AMP, generates realistic noisy masks by attacking the decoder. And contrastive mask refinement learning, or CMRL, models the relationship between the ground truth, the noisy input, and the model's own prediction, using a tri-directional contrastive loss. AMP injects learnable perturbation embeddings into the frozen decoder, and updates them with FGSM-style adversarial steps in embedding space. A guidance mask controls the error type, expansion produces false positives, contraction produces false negatives, and inversion mixes both. An adaptive threshold keeps generating noise until the mask's IOU with the ground truth lands in a target range, so we can precisely dial the difficulty. Because the gradient is largest where the decoder is least confident, the damage naturally concentrates on hard boundaries and ambiguous regions. CMRL splits every pixel into 6 regions based on the ground truth, the noisy mask, and the refined mask, correct regions, successfully corrected failures, and remaining failures. A tri-directional contrastive loss pulls failure features toward correct features of the same class, pushes foreground and background features apart, and lets the model learn from its own successful corrections elsewhere in the same image, creating a self-improving bootstrapping signal. On Coco, Phoenix consistently beats SegFix, BPR, SegRefiner, and SamRefiner. When refining very noisy pseudo-labels from weakly supervised models, we gain up to plus 16 points in mask, AP. And across 7 modern instance segmentation architectures, from mask-RCNN to mask-to-former, Phoenix delivers the largest and most consistent improvements among all refiners, in both mask, AP, and boundary AP. On the DIS benchmark, which demands pixel-precise boundaries for thin, intricate structures, Phoenix improves IOU by 11 to 21 points over the strongest baselines, across for backbone models, and 5 test splits. It recovers fine details like bicycle spokes and ladder rungs that competing refiners smooth away or miss entirely. Beyond refinement, Phoenix is a drop-in add-on for frozen, even proprietary, models. It upgrades noisy pseudo-labels and coarse human annotations into cleaner supervision. And it can be called on demand as a tool whenever a quality check flags a low-confidence mask. It also generalizes zero-shot, without any fine-tuning, to semantic segmentation, cityscapes, and even medical imaging. To summarize, adversarial perturbation can be a constructive tool, not just a destructive one, for building realistic training noise. Combined with tri-directional contrastive learning, Phoenix sets a new state-of-the-art in mask refinement. Code and the project page are at phoenix-eccv26.github.io. Thank you.